points. So choose the correct appropriate graph. Hopefully everybody got that right. For us, it looks like that. The next thing they want you to do is go through and find slope. Okay. And what I want you guys to realize is when we do slope, okay, what is the formula for slope?
Y2 minus Y1, X2 minus X1.
Okay, so slope, yeah, Y2 minus Y1 all over X2 minus X1, right? Okay. We also know, and this is a good thing to start doing, is to recognize other formats for formulas. Okay. I told the last class that I've got some physics students that take my college algebra, and they present me questions about their physics to help them with, and they've got some formulas, and they don't understand the formulas. But when I break the formula down and I tell them that this formula that you're using right now is the same formula that you learned in geometry, it's just written using different notation, things make so much more sense to them. Okay? So learn different formats, because when it's provided as a different format, you can understand what to do. Okay? So delta y and delta x, that just means change in y or change in x, and it just simply means subtract your y's, subtract your x's. So we're going to do that for these two lines. I think they want what? Line AE and BD. So I'll say slope of AE, and then we'll do slope of BD. Okay, now, when we do slope, okay, how many points do you need to do slope?
2.
2. Doesn't matter which 2 you choose.
Nope.
No. As long as they are on the line that you're interested in, it does not matter. So, what I'm going to do here real quick, just to kind of prove a point to you, if I choose, let's say, that point there and that point there, okay, I'm just going to call this one, call it X1, Y1, and we'll call this one here X2, Y2. Okay, so that's all I'm going to identify those coordinates as. So no matter where they're at, okay, I should be able to determine the slope between them. So I'm going to write an equation here real quick that helps us find the slope. Slope means y2 minus y1, right? So I'm going to take the y value, the y value from this point here, okay? So the y value from F, the y value from F, and I'm going to subtract from that the y value from this point right here, which is C. So y value of C. So that is the way in GeoGebra I would say y2 minus y1, okay, for specific ordered pairs. I'm then going to do the same thing for the x's. So it's going to be the x of F minus the x from C. And hit enter. And it gives me this number right here. But that number is simply y2 minus y1 over x2 minus x1. Does that make sense to everybody? Now here's why I did that. If I take these 2 points, that formula is using the x and y values from those 2 points. Okay? So it's using that x value, that y value, and that y value. It's subtracting them and then dividing them. And when I do that, we get -4. Now when I change the points, okay, and I should be able to change either one kind of independently, but does that -4 ever change?
No.
No. So no matter where those 2 points show up, the slope of the line that they are on is always -4. And that's what we learned. That's one of the key things that you learned in algebra last year, is that the slope of a line is constant, meaning that it does not change wherever you are on that line. If I want to get from the top red point to the bottom red point, I'm going to go from one point to the other using a slope of -4 over 1. Okay. Now, when we do this slope idea, it probably makes sense for us, instead of having to choose just random points on that line, okay, it makes sense probably to maybe choose that point right there because that's the intersection of two grid lines, right? But for us, hopefully you all understood that we're going to simply use the endpoints as x1, y1, and x2, y2. Does that kind of make sense? But you have freedom to use any point that you want to, or any 2 points that you want to that exist on that line. Okay? So I'm going to use A and E. Okay, so the slope of A and E, I'm going to subtract my y's, 0 minus 8. And I'm going to subtract my x's in the same order, 5 minus 3. So it gives me negative 8 over 2, which reconfirms what GeoGebra was telling us that we get negative 4. Okay. Now, what if I did it this way? What if I went 8 minus 0? Then what's the bottom got to be? 3 minus 5, right? This 8 minus that 0, then it's going to be this 3 minus that 5. Now, all it does is puts the negative down there, right? Well, 8 divided by negative 2 is still negative 4. A positive divided by a negative is always negative. So we got that slope. Now we're going to find the slope of BD. So I'm going to go y's, 5 minus 3. And then I'm going to go x's, 8 minus 0. So I get, what, 2 over 8? Becomes 1/4. So here's the questions they ask you, eventually, is to develop a relationship between these two lines, A and BD. So AE and BD are what to one another? If the slopes are... Okay, the slopes are reciprocals, and one's positive, one's negative, right?
Yeah.
So they're opposite signed reciprocals, and that tells you that the lines that they came from, these two lines, in fact, are what to one another? Perpendicular. So we have just found out that there is a right angle there and there. Okay, so we got right triangles. And we could use GeoGebra if we needed to prove that to us. Okay? Huh? The next part says, so we're down here at part C, it says write equations for AE and BD. Now this was a thing that I told you if you struggle with this, there were 3 videos that I wanted you to watch that helps you remember how to do this. Did you? Were they useful? Nope. All right, so we want to find the equation of a line algebraically. And the reason we're going to do this is because we're going to use those equations to basically find out where these two lines intersect, where my cursor is. Now, the hope is that you can look at it and say, well, it's obviously 4, 4, right? But what happens when I readjust my picture a little bit and now that intersection is not at integers, right? That intersection where my cursor is now just to the left of 4. So maybe it's like 3.8 or 3.9. And my y value is just above 5, so maybe it's 5.2 or 5.1, right? I can't just guess when that happens. And I have to have an algebraic way of doing this, okay? And that's what the End of Course exam knows. They know students want to be able to look at a graph and just read the graph, which is good. Okay, we should be able to read the graph and gain information from it, but they know that that's what you want to do, and they know that that's the shortcut that high school students are going to take every single time. So they make questions that are geared for you to miss them if that's the approach you take. Does that make sense? You need to make sure that you know how to do this by hand using algebra. Okay? So what we're going to do is we're going to try to come up with an equation for that line right there, that red line, and an equation for that blue line. Okay? If we can find those equations, that gets us to be able to find that point. Okay? So, to find equations, we talked about in that video that any equations you ever come across, this is going to be kind of your best friend for a lot of the next couple classes that you take. Okay? We call that the point slope formula. Okay? Because you need a point, x1, y1, and you need a slope, m. Okay? So what they want to do is they want to find the equation for AE. I would. So the equation of line AE, we're going to go y minus y1 equals m times x minus x1. And we need the slope of AE, which that's what the first question gave us, right? The first part of this problem gave us. AE, the slope is -4. So where I see m, I'm going to replace it with -4. But we also need an x1 and a y1. And x1 and y1 is simply any point that you know to be on line segment AE. So what is one point that is on line segment AE? Is A on line AE?
Yeah.
Yep. Is E on line AE? Yep. So your choices are to use either that point there or that point there. Okay? So we're going to plug stuff in. All right? So M, we now knew to be -4. X1, let's use A first. X1 is the 5. And Y1 is 0. We're finding the equation of a line. So what's y minus 0? Isn't it just y?
Yeah.
Okay. Now I'm going to distribute this. Gives me -4x plus 20. And there's my equation for AE. -4x plus 20. Now, some people might be saying, well, you used A. How did I know to use A? What if I used E? Well, if you would have used E, you would have had y minus y1. And y1 now using E would be 8. Your slope would be -4. And then x1 would be 3. So we have x minus 3. So we go y minus 8. I distribute the -4, so I get -4x plus 12. I want to solve for y. Whenever we do this, whenever we solve an equation, we want to solve for y. Add 8 to both sides. Does it still give me -4x plus 20? Yeah. Okay. And ultimately, no matter what point I choose off of AE, no matter where I choose, any one of those infinite number points, as long as I have the correct value for x1 and y1, you should be able to get that same equation, -4x plus 20. Okay? Now, the idea is not to choose where I've got this point here. I would not choose that point. Because when I choose that point, if I look at this and I ask it to show me the rounding, that point is simply not really convenient to choose, is it?
No.
Okay? So, okay. The next thing we want to do is we want to write the equation of BD. So let me move this over. So we get that equation. Now we'll write the equation of BD. So I'm going to do the exact same thing. We'll go y minus y1 equals m times x minus x1. Okay? So if I'm using BD, I like to use points that have zeros in them because it makes the algebra a little bit easier. So I'm going to use D. So y minus 3. My slope is 1/4, so it goes there. And then it's x minus 0. This is the reason I like to use zeros. What's x minus 0?
X minus 0 is x.
Right. Okay, so I get y minus 3 equals 1/4 times x, which is just 1/4 x, right? Now what do I do to solve for y? Add 3. So I get 1/4 x plus 3. That's the equation for BD. Okay? Is that doable for everybody? All right. Now here's why they asked us to do that. Our goal is actually to find the coordinates of C. Well, the only way we can find coordinates of C is understanding that point is created by the intersection of the red line and the blue line, right? If you remember back to Algebra 1, when you solve systems of equations, the first way you probably did that is you did it through a graph. You graphed two lines, and then you seen where they intersected. Okay? But then you went through the two processes of substitution and elimination and neglected the graph, and then you talked about the solutions that you got through systems of equations using substitution and elimination. And that should then have been explained to you as being the exact same thing if you were using graphical approach. Okay? So, what does that mean to us? That means if I want to find where these two things intersect, I'm going to go look at this system of equations, and I'm going to solve this system of equations for x and y. Okay? Now, it's in a very easy format here. If those two y's are the same, what's that tell you about these two things? These y's are the same, right? Y is y. What's that tell me about the stuff here in blue? They're equal. Okay, that's the substitution practice that you talked about. We've done it a lot this year so far, but you specifically talked about it in Algebra 1, and that was the first technique you used to solve for the intersection of two lines. Okay, solve a system of equations. Now, I don't like the fraction, so what can I multiply everything by to get rid of that fraction?
2.
No, because this still gives me 1/2.
4.
4. Multiply by that denominator. So, multiply everything by 4. That's going to give me negative 16x plus 80 equals x plus 12, right?
Yes.
Subtract x from both sides to get negative 17x. And I will subtract 80 from both sides, so it gives me, what was that, negative 62? Or sorry, 68. Okay. And then when I subtract those, that gives me x, or sorry, divide those, that gives me x to be 4. Okay, is that doable?
Yeah.
So that x to be 4, what that tells me is the x coordinate of where the red line and the blue line intersect. Would you agree x being 4
Yeah.
would be where that red line and blue line intersect in the x direction? Now I got to find the y direction. So now that I know what x is, can I come back up to one of these equations and plug x in to find y? Which one would probably be easier to do that in?
The first one.
Yep. So we go y equals negative 4 times x of 4 plus 20, which gives me negative 16 plus 20, which gives me 4. So when x is 4, y is 4, and that gives me the ordered pair that I get when I ask GeoGebra what is the intersection of those two lines, the red line and the blue line. Okay. Now, my hope is that you learn how to do that by hand, and you force yourself to go through that process, because like I said, on the unforced exam, that picture's probably not going to be as easy to gain that information as that is. Okay? You're going to have to do the algebraic work to get there. Okay? So the next thing in this question. Yes? Part of this question says, use the distance formula to find A, B, B, C, D, C, and D, E. Okay? So we're going to go through and do that. What became problematic for people in the homework, and I got 7, 8 emails last night from this, is that we didn't know how to simplify our radicals. Okay? So hopefully teach you how to do that here. The distance formula. x2 minus x1 squared plus y2 minus y1 squared. Or you might see it written this way. Delta x, that quantity squared, plus delta y, that quantity squared. Okay? I would hate for you to get to the end of course exam, not have memorized this, and this is the version that they give you on your reference sheet. Okay? So I want to make sure that we understand what that delta means. But they want to find distance of, what, A to B?
Yeah.
Okay, so I'm going to take these 2 points, A and B, and we'll subtract the x's. So what's 5 minus 8? Negative 3, and square that you get 9. And now we'll do the same thing with the y's. 0 minus 5 is negative 5, square that you get 25. So I add those two things together and I get radical 34, right? Okay. Now I'm going to do the same thing for BC. All right, so BC is 8 minus 4. Square that. And we go 5 minus 4, square that, and I get radical 17, right? Okay. Then we'll go do DC. So 0 minus 4, square that, gives me 16. And then 3 minus 4 gives me negative 1, square that gives me positive 1. So I get radical 17. And then the last one is DE. So I go 0 minus 3, square that. And then 3 minus 8, square that. And I should get radical 34, right? Nope, 34. So what's that tell me then about BC and DC?
They're the same.
They're the same. So in the picture, BC, which this point here is actually our C. Okay, so BC to DC are the same, right? We also knew we had right angles in here. And then the other piece of information tells me what about AB and DE? AB and DE were both radical 34, right? So AB, that distance there, and DE, that distance there, are the same. So hopefully you recognize that is a hypotenuse, that is a leg, that is a leg, and that is a hypotenuse. So can we prove that this triangle here on the left is congruent to the triangle here on the right?
Yeah.
Yeah, and that's hypotenuse leg. So that was the purpose of the entire question, of every single part we just did, was to get to the justification that triangle ABC was the same thing as triangle EBC. Now here's the thing. Here's what you're not going to like. On the end of course exam, you're probably going to see a question that says, hey, here's a two triangles with points A at 5, 0, B at 8, 5, D at 0, 3, E at 3, 8. Okay? Justify that triangle ABC is congruent to triangle EBC. And they don't walk you through step by step the things you need to come up with to get there. Does that make sense?
Yeah.
Okay. That's how you would approach every one of these questions. Okay. Now, there was some confusion in what do we do with that radical 34 and that radical 17 when we want to simplify things. Okay. Now, the thing is, this example is really not good because radical 34 and radical 17 are already simplified. Okay. But how do we know that? How can we do some radical work here? So this is important because of how much we're going to use radicals. There will be a point in this class where we go for weeks on end where all we deal with is radical values. Okay? Every single problem will incorporate one. And every single problem when it asks you to do multiple types of algebra to it. Okay? So it's going to be very important to be able to do this. So if you haven't been paying attention yet, please pay attention now. And if you're a person that you know you're not very good at this stuff, do the legwork now. Do the work outside of class on your own to understand radicals a little bit better. Because it's going to make your life so much easier when we're using them inside of every single problem. Okay? So let's say that I have radical, let's go 48. Okay, radical 48. Try to use something different than what we use in the other classes. If I have radical 48, what we want to do is simplify it. Okay? My hopes are that you guys understand what a radical is. Okay? This is simply a symbol. Okay? This is a symbol for a number. When I multiply it by itself 2 times, I get 48. Okay? So that number, obviously you probably used your calculator to do this before. I'm going to go square root of 48. Okay? It's 6.92820.323. Now our TI created 4 doesn't go beyond 9 decimal places, 10 decimal places. But the idea is that number is going to continue forever. and it never ends and it never repeats. That's an irrational number. It's like pi, right?
Yeah.
Okay? Pi, we have to have that symbol, that character, to show pi. Because we can't physically write out the entire number. Does that make sense, everyone? All right, we die doing that. That'll be kind of a boring life. So
You would not die.
yeah. If it never ends and it never repeats,
You gotta write faster.
you would. Okay, you write it fast enough so you do not age.
I don't think.
Okay, so when we simplify this, we want to make sure that we still get a symbol that means this number. Okay, or that provides this number. And the idea of simplifying is to look at the number underneath the radical. We call that number the radicand. Okay, and we're trying to figure out the largest perfect square that divides 48 completely or evenly. Okay, and provides a whole number back to us. Does that make sense? What did you say?
6. I'm 6. 36.
Okay, but does 36 divide 48 evenly?
6.
It's 16 is what we're looking for. Okay. Now, how do we do this? Okay, there's a couple different ways of doing this. Okay, so I want to show you different approaches, and hopefully you find one that's efficient for you. If I want to get a whole number back, what is if I take any two numbers and divide them? Okay, or just let's take any number and start dividing it by something. What would be the first or the smallest whole number that you could get back, other than 1? 2. Okay? And that's what we're looking for here. We're trying to get at least a 2 back. Okay? I want to take 48 and divide it by 36 because it doesn't give me a whole number back. And it's never going to give me a number bigger than 2 back. Okay? So, the way you can approach this is take 48 and divide it by 2. What's that give you? 48 divided by 2, guys. Come on. 24. Okay? Now, what that 24 tells me is that the perfect squares I'm looking for are the ones that are less than 24. So perfect squares that are less than 24 are 1, 4, 9, 16, right? Okay? So what we're doing when I take that half is we're saying these are the only potential perfect squares that when I divide 48, I get at least a 2 back. Does that make sense? Now, I'm never going to try 1 because it just gives me back 48. So we're going to try 3 values. Okay? Now, when I divide 48, okay, divided by 4, does it give me a whole number back? It gives me 12 back, right? Okay? However, and that would work, but it doesn't give me simplified. Because we're looking for the largest perfect square that divides 48. 16 also divides 48 evenly and divides it 3 times, right? So what we do is we say that radical 48 is the same exact thing as radical 16 times 3. Okay? Because if I take 48 divided by 16, it gives me 3, right? So it tells me the 2 factors when I do that division. Okay, now you know a little bit about laws of exponents, right? You guys dealt with exponents last year? Okay. The laws of exponents, I'm not going to get into great deal detail with you. If you watched the video from last period, once they all left and I had a little time after lunch, or before lunch, I kind of walked through the details of this. But it's a situation in mathematics where, I've talked about this before, where you don't necessarily maybe have the best background information and knowledge to understand why we do what we do. For instance, if I get a product underneath a radical, hopefully you were taught last year, you can break that up into a product of individual radicals. So I can write this as radical 16 times radical 3. You can do that, okay? The logic behind that is because of the laws of exponents, which you do know. There's also another rule in there that a square root is actually a 1/2 exponent. Okay? You need that to be able to understand why we can do that. All right? But now, if that's the case, then what is the square root of 16? 4. 4. And then radical 3. 3 doesn't have a perfect square that's less than it. That will divide it. So 4 radical 3 is left over. Now, last year, maybe you went and walked yourself through this procedure. If I had radical 48 You said, okay, I'm going to start dividing that by things. And maybe you said, I'm going to divide it by 2. And that gives me 24, right? And then we stopped at 2 because that was a prime number. This is called the prime factorization of 48. So then I do the same thing with 24, and I divide that by 2. And it gives me 12 here. And then I take 12 and divide that by 2. And all of these should be underneath bracket. And I get, what, 6? And then I take radical 2 and radical 3, right? You remember doing that last year?
Yeah.
And then basically you're probably just circled the pairs of
It was 8th grade.
like numbers in 8th grade. Okay. So what this tells us then is that radical 48 is actually the same thing as 2, that 2 right there, times that 2, times that 2, times that 2, times that 3, right? Any number you can ever think about can always be broken down to a product of prime numbers. Okay? Now, using what we talked about above, is that we could say, well, this all means radical 2 times radical 2 times radical 2 times radical 2 times radical 3, right? Does that make sense?
Yeah.
Okay. Now, if I've got a bunch of radical 2's that are being multiplied together, let me ask you this question. Using exponents, if I gave you like 12 times 12, how could you rewrite that using exponents? 12 squared. Okay? So, why can't I do that here? Why can't I write that as radical 2 squared? Does that make sense? So radical 2 squared there. Are those a group of radical 2's? Right as radical 2 squared? And then I've got my radical 3, right? So I can maybe rewrite it that way. What if I take like radical, let's do a calculator quick. If I give you a radical number, square root, let's say all right, if I give you, square root of 15, hit enter, gives me that number right there, right? What do I get if I square that number?
Oh, 15.
I get back 15, right? So it's like how multiplication undoes division, division undoes multiplication, addition undoes subtraction, subtraction undoes addition, right? Square roots to the power of 2 undo each other. They're called inverses. So,
It's like 3 plus
okay,
3.
if you take the square root of 2, you're going to get like 1.4144 something. If you square that, multiply by itself again, you get back to 2. Okay? So, what we learned, and what we talked about in the past, is that that is going to cancel with that, leave you just 2. That is going to cancel with that, leaving you just 2. And then radical 3 doesn't cancel at all. And what's 2 times 2? 4. 4. And I get 4 radical 3, which is exactly what we got up going that way, right? Okay. Now, most of the time, you're probably not going to go through that logic, but I wanted to show you why the algorithm, why when you were taught, hey, circle these two because they're a group of 2 and they come out in front. Circle those two because they're a group of 2 and that number comes out in front. Everything's multiplied together and we get 4 radical 3, right? I want you to know why that works. Because if you know why that works, you'll never mess that up, right? Okay. Or you'll never forget that procedure of how you go through and do that. Okay? Does that make sense to everybody? If you understand that with square roots, it's awesome. Because eventually we'll do it with cube roots. We'll do it with fourth roots and fifth roots. The process is the same. Okay? But the cube root, though, you're looking for groups of 3. The fourth root, you're looking for groups of 4. Okay? Because we get those exponents canceled out. That's how you would do that. Is that all right, everyone? Anybody last night get one with a fraction in it?
What'd you say?
You ever get one with a fraction in it? There's like a 90 over 4 that people were getting a lot. Okay? So let's do that real quick. If I have square root of 90 over 4. Now let's do stem 90. Let's go. Let's do 120 over 4. Okay? So 120 over 4. So The same idea applies when we had something like this. When we had last one, 16 times 3 underneath there, right? We can take that as radical 16 times radical 3, correct? So when you have a product underneath the radical, you can break it up into a product of radicals. When you have a ratio underneath the radical, you can break it up as a ratio of radicals. Okay? Which makes the problem a lot easier, because now I can just focus on that 120 and do all the simplification I need to do with that 120. Then I can focus on 4 and do all the simplification I need to do with that 4. Okay? Now, what perfect square do you see inside of 120? Don't even look at the 120, look at the 12. What perfect square do you see inside 12? 4. 4, okay? So you know that 4 will divide that, right?
Yeah.
How many times does 4 go into 120? 30 times, right? Okay? So, the 4 can come out and take the square root of the 4, so let's write this way. You can just rewrite this as 4, radical 4 times radical 30, right?
3.
Well, 12 divided by 4 gives me 3, right? So 120 divided by 4 should give me 30. I might not have said that. I wanted to go back to the 120. So I get 4 times 30. They give me 120, right? Okay. What's the square root of 4?
2.
2. And then I get my 30, right? Now I want to make sure that 30 is simplified. So what number will divide 30?
2.
Okay, 2. And gives me 15, right?
Yeah.
What number will divide 15?
3.
3, and it gives me 5. So 2 times 3 times 5 is the prime factorization of 30. 2 times 3 is 6 times 5 is 30, right? Are there any pairs there? No. And because there's no pairs, it tells me that 30 is not divisible by a perfect square. Think about this. Take 30 and cut in half, right? It gives you 15, right? The perfect squares that are less than 15 are 1, 4, and 9. Do any of those divide 30 evenly? No. Okay? So the 30 is already simplified. Okay? So I dealt with the top. Now I'm going to deal with the bottom. What's radical 4? 2. So I get to this, right? Now does that simplify? Yeah. Because we can rewrite this as 2 over 2 times radical 30 over 1. Now you don't see the 1 here, but I can multiply by 1 as many times as I want, right? If I take 2 over 2 times radical 30 over 1, multiply those as fractions, so top times top, bottom times bottom, does it give you 2 radical 30 over 2? Okay, what's 2 divided by 2 though? Nope. 1. So that goes to 1, which is why we usually just do that there, cancel it, and you're left with radical 30 as your answer. So, radical 120 over 4 turns into radical 30. Okay? Maybe not the greatest example because if you look at the 120 over 4 real quick, you can simplify that first, right? If I look at 120 over 4, can I simplify that to radical 30 right away?
Yeah.
All right, so there's multiple approaches. I think the one in the homework was like 90 over 4. Okay? I can't simplify that real quick, right? I can change to 45 over 2 if I wanted to. But radical 45 over 2 is not my final answer. I'm going to have to go a little bit further. If you are a person that struggles with radicals, you know yourself a little bit better than I do, right?
Yeah.
I know where we're going after this chapter and the next chapter and the next chapter. Okay, I've seen it probably about 15 years in a row. Okay, you're gonna need to know this stuff. You're gonna need to be able to work with radicals. So, on my website, if you're a person that knows you struggle with it, and now you know how much we're going to use it, come down to the bottom here. And there's a link that says radicals. Click on that. There's going to be a series of GeoGebras that allow you to practice an infinite number of these simplification processes. But then, if that doesn't do what you need it to do, there is a series of videos here at the bottom, once it loads, that walks you through, okay, 12 videos there? There are about 12 videos, 16 videos almost. I think it's 14 actually. Of people walking you through step by step the algebra for simplifying radicals, adding radicals, multiplying and dividing them, doing it with fractions. A very good thing to look at and make sure you have a good understanding of because of what we're going to do later on. Okay, we're going to soon learn a